All right, let's jump right into one of the absolute biggest hurdles in AI right now. We all want models that can process huge amounts of information, like entire books or massive code bases. But how do you give an AI a basically infinite memory without the computational costs going through the roof? Well, today we're going to look at two very different and, frankly, brilliant solutions to that exact problem.
And this question, right here, it just perfectly sets the stage for everything we're about to talk about. See, instead of just throwing more and more hardware at the problem, the really smart folks are asking a much deeper question. Can we make AI memory smarter, not just bigger? And that question is going to take us down two fascinating paths, one inspired by the human brain and the other by the actual physics of the computer chips themselves.
So to really wrap our heads around the solutions, we first have to understand the problem. Why is it so ridiculously hard to give AI a long-term memory? Well, it all boils down to this one critical concept, the context window. Think of the context window as an AI's short-term attention. It's everything it can look at all at once to figure out what to say next. Now, you'd think, simple, just make the window bigger. But here's the catch. When you expand that window, the amount of computation needed doesn't just grow, it literally explodes.
And this slide lays out the classic dilemma perfectly. On one hand, you've got your modern transformers. They have flawless, perfect recall of everything inside their window. But their memory use is massive, and the compute cost grows quadratically. That means if you double the context window, the cost doesn't double, it quadruples. It gets out of control so fast. On the other hand, you had older models like RNNs. Super cheap to run, but they compress everything into a lossy summary, meaning important details just vanish. So for years, you had to choose perfect memory or efficient memory. You couldn't have both. Until now.
So for our first solution, where would you look for inspiration? Where else? You look at the most efficient information processor we know of, the human brain. It turns out nature already solved this exact problem millions of years ago.
What's so incredible is how elegantly the brain handles all this. It's not just one giant hard drive. No, it's a super sophisticated multi-store system. Your prefrontal cortex gives you that perfect, high-definition short-term memory. Then, you have the hippocampus, which acts like a buffer, grabbing new experiences, and later it cleverly compresses and transfers the important stuff, the general ideas, into your long-term memory in the neocortex. It's why you can remember the plot of a book but not every single word. It's the absolute best of both worlds, high fidelity and high efficiency. So, taking this blueprint directly from nature, researchers built something called the Artificial Hippocampus Network, or AHN. And the goal is simple, really. Create an AI memory system that works just like our brains, combining that perfect short-term recall with an efficient, compressed, long-term storage.
And here's the genius of how it works. The AI uses a normal sliding window for its short-term memory, perfect lossless recall of what just happened. But, and this is the amazing part, just as old information is about to fall out of that window and be lost forever, it gets caught by this artificial hippocampus. This efficient module creates a smart summary of it. So the AI gets to see two things at once, the crystal clear recent past and a really good summary of the distant past.
So what happens when you build an AI this way? Well, when they tested it on a document with over 100,000 tokens, that's a lot of text, this brain-inspired approach shrunk the memory needed by a staggering 74%.
But here's the real kicker. It wasn't just more efficient, it was actually smarter. On a key long-context benchmark test, the model with the artificial hippocampus didn't just keep up, it blew the original model out of the water, all while using way fewer resources. So just think about that. By mimicking the brain, the AI got both leaner and more capable. That's a huge win.
Okay, so that was the biology-inspired approach. Now let's pivot and look at a completely different philosophy. What if the problem isn't really the AI's architecture at all? What if the real bottleneck is just a simple traffic jam happening inside the GPU? So every GPU that's running these models has two types of memory. You've got a tiny amount of on-chip SRAM that is absurdly fast. Then you have a huge pool of what's called high bandwidth memory, or HBM, which is, it's much slower. The problem is standard AI attention is constantly reading and writing massive amounts of data back and forth from that slow HBM. And it's that round trip, that traffic jam that's slowing everything down, not the actual math. This insight sparked a whole new way of thinking, creating what are called I/O-aware algorithms. The goal here isn't just about doing fewer calculations. The real goal is to dramatically cut down on the number of times you have to make that slow trip to HBM. And this simple idea is the secret behind our second amazing solution, flash attention. So how does flash attention get around this traffic jam? It's actually a pretty clever trick called tiling. It breaks the massive attention calculation into smaller chunks, small enough that each one can fit entirely inside that super-fast on-chip SRAM. It does all the math, all the intermediate steps, right there in the fast lane, and only writes the final answer back to the slow memory one single time. No more back and forth, back and forth.
And man, you can really see the difference it makes here. The standard way of doing things involves all these separate steps, each one a slow round trip to memory. But flash attention fuses all of that into one single highly optimized operation, what engineers call a kernel, that runs entirely in that fast memory. The result? The time drops from 16 milliseconds down to less than 3. That's over 5 times faster.
Now, when you zoom out and look at what that means for training an entire model like GPT-2, this one optimization leads to an incredible 3-fold speedup. End to end, you can train your model 3 times faster just by being smarter about how you move data around.
Honestly, this graph just says it all. That scary curve shooting up towards the moon, that's the quadratic explosion of cost with the old attention method. It's unsustainable. And that nice, calm, straight line at the bottom, yep, that's flash attention. By getting rid of all those slow memory trips, it turns the biggest bottleneck in AI from a quadratic nightmare into a simple, manageable, linear problem.
But the story didn't stop there. This incredible hardware-aware idea wasn't a one-off. It was the start of a rapid evolution, with each new version getting smarter and faster by understanding the hardware even better. So Flash Attention 1 gave us that core idea of tiling. Then version 2 came along and basically doubled the speed again by getting way smarter about how it split the work across all the GPU's cores. And then Flash Attention 3 squeezed out another 2x speed up by using some really advanced tricks to perfectly hide the time it takes to fetch data. It just got faster and faster. So we've got these 2 amazing solutions, one from biology, one from computer science. So let's bring it all together. What does this actually mean for the future of AI? Where does this take us? Well, this matters a whole lot, and here's why. This work lets us finally train models that can handle massive contexts, like we said, entire books, entire code bases. It drastically cuts the cost of training, which also means it reduces the carbon footprint. It opens the door to brand new applications in things like video and audio. And it makes building powerful AI models accessible to more people, not just those with the deepest pockets. And I think this quote about the biological approach just captures the bigger ambition perfectly. This isn't just about making things run faster. It's about building models that can genuinely understand, remember, and reason over these vast horizons of information, a lot more like we do. And that right there is the beautiful symmetry in all of this. You have one problem, but 2 completely different philosophies for solving it. One looks inward, to the elegant solution that nature evolved over millions of years. The other looks outward, to the fundamental physical constraints of the silicon it's running on. And it turns out both are incredibly powerful ways to innovate. Which really leaves us with one final thought. We've started to crack the memory problem by learning from the brain and by mastering the machine, and that's unlocking some incredible potential. So the question we're all left with is, what's the next big bottleneck? And where on earth are we going to find the inspiration to break through it?